Implementation of software quality metrics. Software quality metrics are a subset of software metrics that focus on the quality aspects of the product, process, and project. These are more closely associated with process and product metrics than with project metrics. Software quality metrics can be further divided into three categories: product quality metrics, in-process quality metrics, maintenance quality metrics. Product quality metrics. These metrics include the following: mean time to failure, defect density, customer problems, customer satisfaction. Mean time failure. It is the time between failures. This metric is mostly used with safety critical systems such as the airline traffic control systems, avionics, and weapons. Defect density. It measures the defects relative to the software size expressed as lines of code or function point, etc. In example, it measures code quality per unit. This metric is used in many commercial software systems. Customer problems. It measures the problems that customers encounter when using the product. It contains the customer's perspective towards the problem space of the software, which includes the non-defect oriented problem together with the defect problems. Customer satisfaction. Customer satisfaction is often measured by customer survey through data through the 5-point scale. Very satisfied, satisfied, neutral, dissatisfied, very dissatisfied. Satisfaction with the overall quality of the product and its specific dimensions is usually obtained through various methods of customer surveys. Based on the 5-point scale data, several metrics with slight variations can be constructed and used, depending on the purpose of analysis. For example, percent of completely satisfied customers, percent of satisfied customers, percent of dissatisfied customers, percent of non-satisfied customers. Usually, this percent satisfaction is used. In-process quality metrics. In-process quality metrics deals with the tracking of defect arrival during formal machine testing for some organizations. This metric includes defect density during machine testing, defect arrival pattern during machine testing, phase-based defect removal pattern, defect removal effectiveness. Defect density during machine testing. Defect rate during formal machine testing. Testing after code is integrated into the system library. This is correlated with the defect rate in the field. Higher defect rates found during testing is an indicator that the software has experienced higher error injection during its development process, unless the higher testing defect rate is due to an extraordinary testing effort. This simple metric of defects per KLOC or function point is a good indicator of quality. While the software is still being tested, it is especially useful to monitor subsequent releases of a product in the same development organization. Defect arrival pattern during machine testing. The overall defect density during testing will provide only the summary of the defects. The pattern of the defect arrivals gives more information about different quality levels in the field. It includes the following: the defect arrivals or defects reported during the testing phase by time interval, example given week, year, all of which will not be valid defects. The pattern of valid defects arrivals when problem determination is done on the reported problems. This is the true defect pattern. The pattern of defect backlog. Every, Over time, this metric is needed because development organizations cannot investigate and fix all the reported problems immediately. This is a workload statement as well as a quality statement. If the defect backlog is large at the end of the development cycle and a lot of fixes have yet to be integrated into the system, stability of the system, hence its quality, will be affected. Retesting regression tests is needed to ensure that targeted product quality levels are reached. Phase-based defect removal pattern. This is an extension of the defect density metric during testing. In addition to testing, it tracks the defects at all phases of the development cycle, including the design reviews, code inspections, and formal verifications before testings. Because a large percentage of programming defects is related to design problems, conducting formal reviews or functional verifications to enhance the defect removal capability of the process at the front end reduces error in the software. The pattern of base-phase effective defect removal reflects the overall defect removal ability of the development process. With regards to the metrics for the design and coding phases, in addition to defect rates, many development organizations use metrics such as inspection coverage and inspection effort for in-process quality management. Defect removal effectiveness. It can be defined as follows. DRE is equals to defect removed during a development phase over defects latent in the product times 100%. This metric can be calculated for the entire development process. For the front end before code integration and for each phase, it is called daily defect removal. When used for the front end and phase effectiveness for specific phases, the higher the value of the metrics, the more effective the development process, and the fewer the defects pass to the next phase or the field. This metric is a key concept of the defect removal model for software development. Maintenance quality metrics. Although much cannot be done to alter the quality of the product during this phase, following are the fixes that can be carried out to eliminate the defects as soon as possible with excellent fix quality. Fix backlog and backlog management index. Fix response time and fix responsiveness. Present delinquent fixes and fix quality. Fixed backlog and backlog management index. Fixed backlog is related to the rate of defect arrivals and the rate at which fixes for reported problems become available. It is a simple count of reported problems that remain at the end of each month or week each week. Using it in the format of a trend chart, this metric can provide meaningful information for managing the maintenance process. Backlog Management Index (BMI) is used to manage the backlog of open and unresolved problems. BMI is equals to number of problems closed during the month over to number of problems arrived during the month times 100%. If BMI is larger than 100, it means the backlog is reduced. If BMI is less than 100, then the backlog increase. Fixed response time and fixed responsiveness. The fixed response time metric is usually calculated as the mean time of all problems from open to close. Short fixed response time leads to customer satisfaction. The important elements of fixed responsiveness are customers' expectations, the agreed to fixed time, and the ability to meet one's commitment to the customer. Present delinquent fixes. It is calculated as follows. Percent delinquent fixes is equals to number of fixes that exceeded the response time criteria by severity level over number of fixes delivered in a specified time times 100%. Fixed quality or the number of defective fixes is another important quality metric for the maintenance phase. A fix is defective if it did not fix the reported problem or if it fixed the original problem but injected a new defect. For mission-critical software, defect fixes are detrimental to customer satisfaction. The metric of percent effective fixes is the percentage of all fixes in a time interval that is defective. A defective fix can be recorded in two ways. Record it in the month it was discovered or record it in the month the fix was delivered. The first is a customer measure. The second is a process measure. The difference between the two dates is the latent period of the defective fix. Usually, the longer the latency, the more will be the customers that get affected. If the number of defects is larger than the small value of the percentage metric will show an optimistic picture. The quality goal for the maintenance process, of course, is zero defective fixes without delinquency. Limitations of software metrics. Software metrics contains many activities which include the following: cost and effort estimation, product productivity measures and model, data collection, quantity models and measures, reliability models, performance and evaluation models. Structural and complexity metrics, capability and maturity assessment, management by metrics, evaluation of methods and tools. Software measurement is a diverse collection of these activities that range from models predicting software project costs at a specific stage to measures of program structure. Cost and effort estimation. Effort is expressed as a function of one or more variables such as the size of the program, the capability of the developers, and the level of reuse. Cost and effort estimation models have been proposed to predict the project cost during early phases in the software lifecycle. Different models proposed are Bohm's Kokomo model, Putnam's Slim model, Albrecht's function point model. Productivity model and measures. Productivity can be considered as a function of the value and the cost. Each can be decomposed into different measurable size, functionality, time, money, etc. Different possible components of a productivity model can be expressed in the following diagram. Software measurements is a diverse collection of these activities that range from models predicting software project costs at a specific stage to measures of program structure. Cost and effort estimation. Effort is expressed as a function of one or more variables such as the size of the program, the capability of the developers, and the level of reuse. Cost and effort estimation models have been proposed to predict the project cost during early phases in the software lifecycle. Different models proposed are Bohm's Coco model, Putnam's Slim model, Albrecht's function point model. Productivity model and measures. Productivity can be considered as a function of the value and the cost. Each can be decomposed into different measurable size, functionality, time, money, etc. Different possible components of a productivity model can be expressed in the following diagram. Data collection. The quality of any measurement program is clearly dependent on careful data collection. Data collected can be distilled into simple charts and graphs so that the managers can understand the progress and problem of the development. Data collection is also essential for scientific investigation of relationships and trends. Quality models and measures. Quality models have been developed for the measurement of quality of the product, without which productivity is meaningless. These quality models can be combined with productivity model for measuring the correct productivity. These models are usually constructed in a tree-like fashion. The upper branches hold important high-level quality factors such as reliability and usability. The notion of divide and conquer approach has been implemented as a standard approach to measuring software quality. Reliability models. Most quality models include reliability as a component factor. However, the need to predict and measure reliability has led to a separate specialization in reliability modeling and prediction. The basic problem in reliability theory is to predict when a system will eventually fail. Performance evaluation and models. It includes externally observable systems performance characteristics such as response times and completion rates, and the internal working of the system such as the efficiency of algorithms. It is another aspect of quality. Structural and complexity metrics. Here we measure the structural attributes of representations of the software, which are available in the advance of execution. Then we try to establish empirically predictive theories to support quality assurance, quality control, and quality prediction. Capability maturity assessment. This model can assess many different attributes of development, including the use of tools, standard practices, and more. It is based on the key practices that every good contractor should be using. Management by metrics. For managing the software project, measurement as a vital role. For checking whether the project is on track, users and developers can rely on the measurement-based charts and graph. Standard set of measurements and reporting methods are especially important when the software is embedded in the product where the Customers are not usually well versed in software terminology, evaluation of methods, and tools. This depends on the experimental design, proper identification of factors likely to affect the outcome, and appropriate measurement of factor attributes.